team currently. As of 3 months ago, I worked in the home feed team at Pinterest. And so, hold on one second, I can't see the slides myself. I'm going to move the poster. Cool. I've been at Pinterest for around a little over a year. I worked at Uber and Microsoft before this. And today I'm going to talk to you about accelerating development velocity of production machine learning systems using Docker. How many people just woke up from a nap? Well, super long title, and I get it. I'm just going to go ahead and explain what this talk means. We're basically talking about accelerating development velocity that's increasing the pace at which a developer or an engineer can code on production machine learning systems, which is services that back up a machine learning infrastructure. Using Docker, basically we're saying how can we use Docker, or with the help of Docker, improve the engineering velocity of a developer who works on machine learning services. And that's what I did in the home feed team. I was an infrastructure engineer, and our infrastructure basically backed up all the machine learning systems. So that's what this talk is going to be about. A little bit of context. This talk basically uses really, really simple Docker usage and puts it in use for scenarios that are very prevalent in the tech industry or the tech company. I go through it every single day where debugging becomes a big hassle, and I'm sure most of you are developers here. And so if you're in a Java world or a C++ world where you're in a dependency hell, this will come in really handy. So if you're looking for some really fancy Docker usage, that's not what this is about. This is more about putting really simple Docker use to this very, very complicated scenario that most of us go through. Anyway, moving on. How many of you have not heard about Pinterest at all? Great. So Pinterest is a visual discovery engine. What does that mean? We help pinners or users discover the content, discover your interests. And so basically, it's when you land on Pinterest.com, you see a bunch of feeds that are displayed to you. That feed is basically a collection of pins, and those pins are whatever the users told us they like. We've recommended you more of such things. And so getting a little bit into the nitty-gritty, what is a pin, right? A pin is a basic unit of content at Pinterest. And so it is a visual bookmark that the user or the pinner can take from the internet and save it. Save it as on your profile, on your board, right? So what's a board? A board is a collection of such pins. So it's a collection of these units, and a board can go as broad as a board of fashion or a board of style, or it can be as narrow as a board of yellow jackets or yellow scarves. And so the pinners or the users can basically get all these pins from the internet and save it on a certain board. And you can have multiple boards, and pinners can follow each other, follow different boards that are public, and so on and so forth. And then coming back to what is a home feed. So when a user lands on Pinterest.com, when you're signed in, the first page that is shown, that is the home feed. Home feed is our most engaging service, and it also makes up to 40 to 50% of the revenue at Pinterest. So needless to say, it's a very powerful product. It's also the first product that was powered by machine learning. What is the core problem that we're trying to solve in the home feed team? It is predicting the likelihood, the engagement likelihood between a user and a pin. So how likely is a user, how likely is a user going to engage with a pin? That's what we're predicting. And that's where the machine learning aspect of this whole thing comes into play. So that's just one product. Now, giving you a little bit of sense of the scale of Pinterest, right? We have over 200 million monthly active pinners. We serve 100 billion pins every day, which means we serve 3 trillion pins a year. And so needless to say, the product is super complicated, it's super huge, it runs at a very big scale, and given the fact that it has so many machine learning aspects to it, some of them, other than the home feed that I just mentioned, is also called the interest-based feed, are recommendations. So the user tells us what is it that the user likes, and Pinterest picks for you other kind of pins, right? So if the user says that you're interested in yellow jackets, seems to be my favorite, Pinterest might tell you, oh, if you like yellow jackets, you're quite likely to like yellow scarves or yellow pants, for instance. That's recommendations. That's also where we see a little bit of machine learning. Then there's search. Search is where the user types in a search word or a search keyword, and we predict what has the user clicked on a lot from the search results. What should the order be? What should the relevance be? What should the ranking be? That's a big machine learning product here. And then there's ads. A lot of people tell me they didn't know that Pinterest operates on ads, right? That's our revenue-making mechanism. If you look on your home feed or your search results, some of the pins that you see, they have a promoted pin tag on it. Those promoted pins are advertisements on Pinterest. And how do we render those advertisements to you? Same. We take the user signal into account. We see what have you repinned in the past, what are you more likely to repin in the future, and based on that, we recommend ads to you. Then one of the other features is visual discovery. Has anybody here heard of Pinterest Lens? Okay, so if you go to your Pinterest app, on the top right corner, there's a camera icon. That's a camera, basically, that uses the camera of your phone. And if you point it to an object that you like, it'll recommend what that object is, where can you buy it, what are similar objects, what are the stores you can buy it, so on and so forth. And that's a pretty powerful object recognition platform. I do that all the time. I like someone's purse, and I just shoot my Pinterest Lens there, and it tells me where to buy that purse from, for example. So these are some of the machine learning places where Pinterest uses machine learning at. Moving forward, so needless to say, given the scale at which Pinterest is operating and all the ML aspects that I just mentioned to you about, the product is super complex. So how did we get here, right? So going back 6 years, 2012 and before, right? Pinterest was, I'm just going to talk a little bit about the evolution of how we got here. It might help you understand why we migrated to microservices. So 2012 and before, we were a monolith, one single service that did all of this. It was not this complicated at the time, but at the time, Pinterest used to be a chronological feed based on user interests. So the user comes in and tells us, this is what you're interested in, and we literally just pick that data from an inverted index and render it to you. That's about what this was, right? Good enough, but works for a small community that's oriented around similar interests, but doesn't really help the user explore content or discover anything new. So in 2013, we introduced Smart Feed. We introduced ranking and relevance. And then in 2014 and onwards, we basically tried to understand what is the user more likely to click. We took user signal into account. What has the user repinned in the past? What has the user said that they don't like in the past? That's negative signal. So we started taking that. 2015 onwards, we started considering tree-based regression models into machine learning. And 2016 onwards, we basically just got better and better, improved our relevance more and more, improved the order at which we basically rendered the feed to you. So that's how the product evolved. Now, when it was a very small service, which basically all it did is went to the inverted index and got a bunch of pins and rendered it to you, it was super simple. It wasn't a big deal. But when it became this complex, a monolith didn't really work for lots of reasons. Starting with dependency. A single bug in the service would cause the whole product to come down or break down. that wasn't the most ideal, right? Scalability became an issue. You don't want to be scaling services you don't need, parts of the services you don't need, and so on and so forth. And as the company became bigger, the product became bigger, more and more people started working on the service. And so dividing it, modularity became an issue, right? So for all the reasons that other companies moved to microservices, Pinterest moved to microservices. And with microservices came everything that monoliths did not give us, obviously. Modularity, we're able to scale the services the way we wanted to, at the time we wanted to. We didn't have to scale the whole service all at once, which was great. Ooh. What is that? Any guesses what that is on the screen right there? That, right, somebody in my company said that was the food we eat in the cafeteria. And I was like, God, I don't know what you're eating, man. Donkey, seriously? Anyway, these are microservices. I like this analogy a lot because if you see, microservices don't really, they can't talk to each other. They don't know where to look for input. They don't know where to get the output from. They're totally made differently, so on and so forth. They're in different stacks. And so, as you see, bunch of challenges that come with that, right? Like I said, they're in different platforms, in different OSs, they're in different languages. And so having a unified way to have these things, these services talk to each other becomes quite a challenge. And then when you're dealing with microservices, you're really dealing with everything that comes with a distributed system. Microservices talk over TCP/IP and whatnot. One other thing that I wanted to bring up in context of this talk is that a lot of microservices depend upon the same dependencies or the same DLLs, right? So what do you do when two microservices depend on one DLL but on a different version, right? If this has a V1 and this needs a V2, how do you deal with that on your machine? And that's what I'm going to talk about a little bit further as well. But so coming back to a little bit of machine learning here, how do we tie this whole thing into ML that I spoke about a little bit before, is what's a typical machine learning workflow? Like, what does it look like? Right? You begin with generating data and then training that data. And then you build a model out of it. So then you train your model, and then you evaluate it offline, and then you run an online experiment. So that's a very typical ML workflow, right? When you talk about model training, you're basically generating your data, training your model, evaluating your model, testing it, and then rolling an experiment out. And that's a loop. It doesn't happen once, doesn't happen twice. It happens in a loop. You iterate on it over and over again, and then you see whether your model is generating the data over a course of time. That's what model training would look like. So now coming back to the model training aspect and fitting it into the Pinterest home feed, right? That's a typical way of rendering a home feed. What we do is when the user sends a request, we send the request to multiple candidate generators. A candidate is a pin, right? A candidate generator is a service that gives us a bunch of pins. And so, for instance, where all do we get those pins from? There are different services based on what are the topics that the user follows? What are the other users that the user follows? And what are the recommendations that Pinterest has picked for you? We gather those services and we put them in a ranking model. Now the ranking model is where the model training aspect of this whole thing happens. And once the model is deployed there, we basically render the home feed. The model does a bunch of fancy things, it could be based on anything, and then in the policy layer, we basically try to do a little bit of relevance, a little bit of ranking, we order it, we filter it, we take the spam out, and then we display the home feed. So that's what a typical home feed ML workflow looks like. Now, I do want to go into this a little bit. So let's talk about this from the left-hand side. So the API layer is when the user goes to Pinterest.com, signs in, and hits home feed. That's when the request comes in. Now, when the request comes in, the request goes to the smart feed service. That's the SF service right here. And then the non-materialized generator, think of it as a cache. And the materialized store is not the cache. It's the place where pagination happens, which I'll talk about in a little bit. But the request goes to the smart feed service, And then the smart feed service asks the non-materialized generator, which is also the cache, does this user's home feed exist here? If the answer is yes, it's returned. If the answer is no, then the smart feed service goes to the SF generator service, which is the smart feed generator. That's the place where the model is deployed, by the way. Now, the smart feed generator goes to these candidate generators. The candidate generators get candidates from these different services. Now, these different services are backed up by databases where the actual content lives. And once it gets all the pins, it returns it to the generator. That's where the model is deployed, like I said. It does a bunch of model magic. And then it sends it to the materialized store. And it writes it there. It writes the data to the materialized store. The reason we write it is because, say you're on the first page of your home feed. What the materialized store returns is the first 5 pages of your home feed. And then when the user scrolls further down to the 6th page, we again make that service, and the materialized store again gives you the 6 to the 10 pages. That's called pagination, right? That's how this whole thing works. And there's a lot of complication here in terms of, there are a bunch of other services. I've just abstracted this whole architecture for simplicity of this presentation. But lots of these services use common services. Like I said, there are databases that are backed up by candidate generators and so on and so forth. So now if you think about this, imagine the smart feed service and the smart feed generator. Those two services are very likely to be dependent upon a bunch of DLLs, a bunch of common DLLs, a bunch of common packages, and they might very well need different versions of it, right? You don't want to be dependent upon the version of that. So if you're on your dev machine or if you're on your local machine, how do you deal with that? When 2 to 3 services need the same DLL, but a different version of the DLL. That, to me, seems like a very tricky problem, right? So that's one aspect of it. The other aspect of this whole thing is that when you deploy the model in the SF generator service, how do you test this thing? How do you test an end-to-end workflow where the user sends a request and what's returned is what the model is supposed to return? How do you test that, right? So the way I would test that in the past is I would basically deploy a bunch of the, install a bunch of these services on my local machine, have them up and running, and then send a request to API, and maybe have some of these services make production requests. But that's not always feasible, because if the smart feed generator was in production, how do you really test your model? There's no way to do that. And if there is, it's super complicated. Takes just so much time away. And so what do you do? When you deploy the model and you want to test it, how do you debug that, right? That is when we decided to use Docker here, where it's basically going to let the applications run in isolation with each other in containers. So anybody have no idea what Docker is here? Cool. So Docker is name of the company. It also produces the software called Docker, and it is a containerization platform. So what does that mean? It bundles applications with its dependencies and packages and its runtime environment and puts them in a container. It also runs on its own network interface, right? If you know what virtual machines are, some may argue that Docker or containers are very similar to virtual machines, but some might be like, oh no, it's not similar to virtual machines at all. It's very, very different. So I'm gonna go a little bit into that as well. Now, containers are super lightweight. They are an abstraction on the application layer. And virtual machines are an abstraction on the physical hardware layer. So the hypervisor, as you see, that is one server which divides into multiple servers, and each server is a virtual machine. So each virtual machine has its own copy of the operating system, right? Has takes tons and tons of space. And it's not as lightweight as a container. Container, on the other hand, like I said, is an abstraction on the application layer and does not have a copy of its own OS. And so starting and stopping a container is also super easy. It's a super lightweight thing, right? So getting the best of both worlds, I would say, put containers into virtual machines. You basically get an abstraction on the physical layer, and inside that you have abstractions on the application layer. That's basically the best usage of all your resources from an infrastructure standpoint. So now coming back to what a Docker workflow looks like. It's really three things. You have a script that gets your service up and running, right? You put that script in something called a Docker file, which is a text file of instructions. That text file is understood by the Docker daemon for compilation. And so those instructions are understood by the Docker daemon. We'll go into that a little bit we'll go into that a little bit further. But you build a Docker file in order to make a Docker image. And a Docker image is a snapshot. It's a snapshot of your application bundled with all the packages in the environment it needs to run in, right? And this Docker image ultimately runs inside a Docker container. So that's what it is. It's really a three-step process. You write the Docker file, you compile it into a Docker image, and then you run the Docker image into a container. Now, that's what a Docker file looks like. It might not be very visible to you, so I'm just going to read it out. There are certain instructions. There are lots of other instructions that you can use. You can go to the docker.com website. They have all this in detail quite a bit, but I'm just going to give you a little brief of what this is. So the from instruction, it's basically telling you where the base image is from. So every image that is generated on top of the base image, and that's where you take the base image from. env is the environment variables for your script or for your image that you want to build. Work directory is the directory that the container will start in. So if you want to log into your container, whenever you do, you'll land into this work directory. That's what that means. Arguments and add, they both basically do the same thing. They are arguments to your scripts. If your script or your image needs any parameters, that's how you pass it in, right? CMD is the command that the Docker file will run in order to get your service up and running. There's a very similar instruction for CMD. It's called the run command. The only difference between CMD and run is that CMD does not execute at runtime. That's the only difference between the two, but they basically do the same thing. So that's what a Docker file looks like. Now this is great, right? This lets you write a Docker file for one application and then run it in a container. So now you have one container for one application up and running. But more often than not, that's not a very realistic scenario. You're not concerned about debugging one service, right? That's pretty simple to do on your machine. You're most likely thinking of debugging a set of services together, and you want to test your end-to-end workflow. You want one service that calls the other service that calls the third service. And that's the scenario you're most likely going to want to test. So how do you do that using Docker, right? So to that, we have something called Docker Compose. It's a super simple, super easy way to connect and link all these services together. What it does, that's what a Docker Compose file looks like. What you're going to do is you're going to create a YAML file in your root directory. It can be called dockercompose.yaml. And this file contains all the services one after the other that you want to link with each other. So in this file, for instance, I have 3 services. There's a Smart Feed service, there is a Pinnacle 2 service, and there's a Fantasio service. Now, there are a bunch of things here, right? There are ports, if you see. What that means is it's saying that map this port, 5002, on my Docker container to port 9191 on my host machine. And the reason you do that is that multiple containers can run on a single host machine. So you want to mention on which port on your host machine will a certain Docker container run. That's what the ports is, and that's super important, and that's a necessity. It's not optional. Then you give it a container name. It should be unique and something that you understand, because that's the container that will stop, and then you can start it whenever you want to run it the next time. Volumes are directories that you want to mount from your host machine to your Docker container. So for instance, if you want a certain directory, in this case, I have mounted the entire server set and the config directory from my host machine onto my Docker container, just in case you have some paths that you want to access. And then environment is environment variables. So that's what, this is basically, think about a Docker file for each service. You're compiling all Docker files into one service, into one file, and that's called the Docker Compose file. Now, one thing that's really cool that is not on this file is links. Links and depends on. Those are two fields in a Docker Compose file that lets you mention which service links to which service depends on which service. So for instance, my if I send a request to a smart feed service, which in turn makes a request to the Pinnacle 2 service, what I will do here is I will just say that the smart feed service links to the Pinnacle 2 service. And I will show that to you in a demo video that I have. But I wanted to show you a demo, but my laptop is not able to work here. So instead, what I'm going to do is I'm going to show you a video of the demo that I had demoed in the past. And it's very similar to what I would want to show you, but I'll walk you through it too. So, all right. So here, I'm basically on my terminal, and I'm getting into my development machine. It's a dev app. And going into my directory. Not sure if you can see or not, but is that too small? Yeah. Sorry, I don't know what to do here, but anyway, if you can't see it, then ignore that. I'm just going to walk you through it anyway. This is basically what I just showed you was a Docker file. And then now what it's doing is it's building the Docker file by using Docker build. -T was where it gave it the Docker container name or the Docker image name. And then you basically point it to the Docker file that the image is going to be built off of by using the -f command. And now what it's doing, it's just building it. And it takes a few seconds to do that because it's actually executing one instruction after the other in that order mentioned in the Docker file. And then meanwhile, what I'm doing is I'm going to a different tab, getting again into my dev machine, and then I will show you here that Docker PS lets me see all the images and all the containers that are up and running. Now this is a Docker Compose YAML file, where there are all the services that I mentioned to you. So if you see there's links, and then there is depends on right here. And that's basically saying that this service links to the Fantasio service, and then the Fantasio service links to the third service. That basically means that when you do Docker Compose up, that's the file you will use in order to get the Docker Compose file up and running. All these services will get kickstarted. So that's what I'm going to do next in this video. Those are the ports that I showed you, where a certain port on the Docker container maps to a port on the host machine. And like I said, that's super important. Make sure that no ports are overlapping, because only one container can talk on a certain port here. And then that's the links and depends on. This video is a little out of sync to what I'm saying. But then there's a Docker file path that's mentioned there. And once right, and then once you do Docker Compose up, you will see that all these three services, Pinnacle 2, Fantasio, and Magic Box, that's a third service here, will start. And I'm just going to forward this a little bit. So here, this is where I'm doing Docker Compose up. And if you see, certain services that haven't been built do get built. And so that's when Docker Compose up basically says it's starting Magic Box server, Fantasio, and Pinnacle 2. It takes a little bit of time for, if the images haven't been built, it'll build it for you. And if they have been built, it'll basically use the same image that, that was generated. So if you see here, all the services are running now, and they take a while. In the case that a certain service crashes, you'll see a stack trace there, and you can go and debug that, right? One of the ways to see what are the images that actually are successfully created and are up and running is to go to Docker PS, like I said. The services that crash will not have images that are up and running. So that's a good sense into what really is working and what is not working. Another way to look at Docker images are just go to Docker images. -A will give you a list of all the images that are running and are not running. So there are a bunch of ways to debug this. You can ultimately even do docker run -it and your image ID. That'll take you into a bash prompt, which logs you into your root container. And in your root container, you can actually go and see all the logs, the reasons why your service is not running, are the volumes mounted correctly or not, and so on and so forth. But that is really what the demo is about. And there's like I said, there's a lot to this. I don't know how to present this. There's a lot to this Docker demo where you can use inspect in order to see the status of the Docker container. You can do attach to. You can do attach to attach your terminal output to your Docker container output. You can do exec. That is basically getting you into the Docker container to look at more detail to see if your volumes were mounted or not, if the environment variables are correct or not, right? To go and look at your stack trace, to go and look at your logs. And then pause, stop, and remove are pretty intuitive. You can do all of that with your image containers. And then top. Top is a command which will give you process stats of your container, the top process stats. But like I said, the docker.com website has a lot of information on how to go and debug this. It's very intuitive, it's very clear. But this is the use case that a lot of developers run into in tech companies where debugging becomes a big hassle and end-to-end workflow, testing the end-to-end workflow becomes a nightmare because of the dependency hell that we all live in. But that's about what I have, and if you are more interested in this, I've done a podcast. It's called the Software Engineering Daily Podcast. It's the same topic as this talk. It tells you a lot about Pinterest and how we use Kubernetes, how we use Docker in production, and so on and so forth. And I'm also writing a book on the same topic. It should be out sometime in July. That'll go into a lot of depth on this particular topic if you're interested. But otherwise, that's all I have. I'll bring it up for Q&A. And if you have any questions, I am at kinnary@pinterest.com. So feel free to shoot me an email, or I'm happy to take any questions right now as well.
Okay.